China just shocked the world with what they're building. But here's what no one's talking about. While Western media keeps you distracted, China's quietly racing ahead, building a future that looks straight out of science fiction.
A family in Texas waits 18 months for their house, pays $400,000, watches costs climb every single week. In Mexico, engineers just built 50 houses in 4 months, $4,000 each. Not shacks, 3-bedroom homes with concrete walls 8 inches thick. Everyone thinks China owns construction speed, skyscrapers in weeks, entire neighborhoods overnight. The world can't compete. They're wrong. While everyone watched China, 14 countries were testing something different, not faster versions of old methods, different methods. Denmark built a 60-unit apartment building in 3 weeks. Japan replaced a 400-foot bridge in 6 hours without stopping traffic. In 2019, officials toured these sites. One called what he saw impossible. Then the data came back. Construction technology funding tripled globally in 6 months. The race isn't over. China isn't winning the way you think, and what's being built right now makes everything we just mentioned look slow. Here's what changed. For years, the numbers coming out of China seemed unbeatable. Changsha, a 57-story building, rises in 19 days. Not the frame, the entire structure. Windows installed, elevators working, ready for occupancy. The world watches the time-lapse videos. Construction that should take 18 months condensed into less than 3 weeks. Then 2020 hits. COVID spreads through Wuhan. The government makes a decision. Build 2 hospitals from nothing. Huoshanshan Hospital, 1,000 beds, built in 10 days. Leishanshan Hospital, 1,600 beds, built in 14 days. Cameras stream the construction live. Millions watch around the clock. Excavators arrive on empty land. 10 days later, patients receive treatment in completed hospital rooms. The videos go viral globally. News outlets call it impossible, then miraculous, then intimidating. China's method? Prefabricated modules, thousands of workers on rotating shifts, government authority to cut through every regulation, centralized control eliminating delays. By 2022, China's built more modular housing than the rest of the world combined. Not even close. They're building entire cities using prefab methods. The government makes it mandatory. New construction projects must be 30% prefabricated minimum, not a suggestion, a requirement. Their supply chain advantage is total. Chinese companies control the materials. They build the robotics. They manage the construction. Vertical integration from concrete mixing to final assembly. Belt and Road Initiative projects spread these methods across 60 countries, Africa, Asia, South America. Chinese construction technology follows Chinese infrastructure investment. The scale is overwhelming. The speed is documented. The cost advantages are real. Every other country sees the same conclusion. China dominates construction innovation. The gap is widening. Catching up seems impossible. But that conclusion misses something critical. China's methods have one weakness. It's the same limitation that's kept these buildings out of most Western countries. And that weakness created an opening. The weakness? China's speed comes from scaling up old methods. More workers, more shifts, more government control, faster execution of the same basic process. They're building the way humans have built for decades, just more efficiently. Engineers in 14 countries asked a different question. What if we change the process entirely? Not more workers, different workers. Not faster assembly, different assembly. Not improved materials, revolutionary materials. While the world focused on China's hospitals, other innovations were happening quietly. Mexico, Netherlands, Singapore, Japan, Germany, Denmark, UAE, Switzerland, Sweden, Iceland, Australia, South Korea, United Kingdom, Different countries, different approaches, same goal. Make construction fundamentally different. The competition breaks into categories. UAE leads in buildings per capita using 3D printing. Small country, massive adoption rate. They're printing everything from homes to government offices. Netherlands leads in policy innovation. They've rewritten building codes specifically for modular construction, removed regulatory barriers other countries still fight. Singapore has the highest percentage of automated construction. Robots handle 60% of repetitive tasks on major projects. Humans supervise, machines execute. Japan dominates earthquake-resistant innovation. Their techniques combine traditional engineering precision with cutting-edge materials. Safety record unmatched. Germany pushes biological building integration, living walls, self-regulating systems, buildings that function like organisms. China still leads one category, scale, pure volume. They build more, faster, across more locations than anyone else. But that's one category in a multi-category race. Three core technologies stand out. They're not theoretical, they're operational. Families live in these buildings. Vehicles cross these bridges. The structures have years of proven performance. First technology eliminates nearly every step of traditional construction. A machine most people have never seen. It doesn't lay bricks. It doesn't pour concrete into forms. It prints entire walls, layer by layer, like a giant robotic arm squeezing frosting. And it just built a neighborhood in Mexico that survived 2 major earthquakes with 0 structural damage. Picture a robotic arm the size of a crane. It moves on metal tracks around a concrete foundation. From its nozzle, concrete flows, thick, controlled, precise. The arm traces the outline of a wall, then another layer on top, then another. No bricks, no blocks, no wooden forms, no human hands touching anything, just concrete stacking itself into walls. Austin, Texas, 2020, a company called Icon prints a 2,000 square foot house. Start to finish, 27 hours. The concrete mixture hardens as it prints. By the second day, the structure is ready for windows and electrical work. A traditional build for the same house takes 4 to 6 months minimum. This machine did it over a weekend. The precision is what nobody talks about. Every layer lands exactly where the computer calculates. No gaps between materials, no human error, no measurement mistakes, no weather delays stopping work. The walls come out smoother than traditional construction could achieve even under perfect conditions. Cost breakdown, $10,000 in materials and machine time. The same house built traditionally runs $200,000 in construction costs alone. But speed means nothing if the buildings collapse. Skeptics said the same thing. Printed concrete sounds experimental, untested, risky. Then the data came in. Tabasco, Mexico, a neighborhood of 50 homes, all 3D printed, built in 4 months for $200,000 total. That's $4,000 per house. These aren't temporary shelters, full houses, 2 bedrooms, bathroom, kitchen, living room, concrete walls 8 inches thick, metal roofs, proper foundations. 3 years after construction, 2 earthquakes hit the region, magnitude 6.1, then magnitude 5.7. Engineers inspected every home after each quake. They measured cracks, checked foundations, tested structural integrity. 0 damage, not minor damage, 0. Hurricane-force winds, 0 damage. Temperature swings from 35 degrees to 105 degrees, no cracking. The families living there have been interviewed multiple times. No complaints about structural issues, no leaks, no settling problems, no failures. The concrete is actually stronger than traditional mixing. The printing process removes air pockets. Traditional concrete often traps air during pouring and vibrating. Those pockets create weak points. Printed concrete has consistent density throughout, layer bonds to layer with uniform strength. China saw the potential. 2018, a company called Winsun printed a 5-story apartment building in 1 week.
Not the frame, the entire structure, including curved architectural details that would take months to build with traditional methods. The building passed identical safety inspections as conventionally built structures. Same fire codes, same earthquake standards, same insulation requirements. It just finished 90% faster. But 3D printing has limitations nobody advertises. Rain stops the process completely. Water interferes with concrete curing. Cold weather below 40 degrees creates bonding problems between layers. Extreme heat above 95 degrees causes cracking as layers dry too fast. Architectural customization is limited. The printer follows programmed paths. Complex curves and details require sophisticated programming. Most printed homes look similar because templates are reused, and the technology requires significant upfront investment. The printing equipment costs $250,000 to $500,000. Small contractors can't afford entry. But even with these limitations, 3D printing solves one major bottleneck: building the structure. It doesn't solve foundation work, utility installation, site preparation. The next technology eliminates even those delays. Imagine a hotel room built inside a factory. Walls, ceiling, floor, bathroom completely tiled, kitchen cabinets installed, furniture in place, TV mounted and wired, artwork on the walls, everything complete. Then imagine lifting that entire room with a crane and stacking it like a shipping container. That's modular construction, and it just built a 168-room hotel in 48 hours. Sweden, 2017. Each room manufactured in a climate-controlled factory 200 miles from the site. Plumbing installed, electrical done, beds made, curtains hung, even toilet paper in the dispensers. The modules arrived on trucks. Cranes stacked them 8 stories high. Workers connected the utilities between modules, sealed the joints, completed exterior finishing. Guests checked in 2 days after the first module was placed. Traditional timeline for that hotel, 16 months. The cost difference is staggering. That Swedish hotel cost $8.2 million total. A conventional build for the same specifications runs $18 to $22 million. The savings come from factory efficiency. No weather delays. Rain doesn't stop production. Snow doesn't slow workers. Heat doesn't create safety concerns. The factory runs 12 months a year at consistent productivity. No theft from construction sites. Materials stay secure inside a controlled facility. Tools don't disappear. Copper wiring doesn't get stolen overnight. No workers standing around waiting. Traditional construction is sequential. Framers wait for foundation crew. Electricians wait for framers. Drywall crew waits for electricians. Constant delays as each trade waits for previous tasks to finish. Factory assembly is parallel. Multiple modules build simultaneously while the foundation is being prepared. When the foundation is ready, modules are already complete. Denmark took this further. Social housing project. 60 apartments for low-income families. Empty lot to families moving in, 3 weeks. Each apartment arrived complete. Kitchen appliances installed, bathroom tiles grouted, floors finished, paint on walls. The buildings meet identical safety codes as traditional construction. Fire resistance tested, earthquake standards verified, insulation requirements exceeded. Just assembled like furniture instead of built from scratch. Cost, $80,000 per apartment. Traditional construction in Denmark runs $180,000 to $220,000 per unit. 60% savings. But modular construction carries a stigma. Post-World War II housing shortages created demand for fast building. Governments erected prefabricated housing projects. Many were low quality, thin walls, poor insulation. They deteriorated quickly. Prefab became associated with cheap, temporary, low-income trailer parks. That perception persists. Developers building modular housing design exteriors to look traditionally built. They hide the construction method. Resale value concerns are real. Buyers worry about long-term durability. Banks hesitate to provide mortgages. Appraisers don't know how to value these properties. Insurance companies charge higher premiums for unproven methods, even when the buildings meet identical safety standards. Building codes create barriers. Regulations are written for stick-built construction. Modular projects require special approval processes, delays that eliminate the speed advantage. Construction unions oppose automation. Jobs disappear. A factory with 50 workers replaces 200 on-site workers. Union political pressure slows adoption in many regions. and customization is limited. Modules must fit standard dimensions for trucking, highway width restrictions, bridge weight limits, tunnel height clearances. Most modular buildings look similar because templates are reused. Architectural variety costs more as custom modules require unique engineering. China recognized these challenges and solved them differently. Vertical integration. Chinese companies own the factories. They manufacture the materials. They build the transport trucks. They control the entire supply chain. Government mandates override union opposition. The 30% prefab requirement forces adoption, regardless of resistance. Belt and Road projects export this model. Chinese companies build modular infrastructure across Africa and Asia. They're not just selling buildings, they're selling the entire system. But Netherlands leads policy innovation. They rewrote building codes specifically for modular construction, streamlined approval, standardized inspections, created mortgage products for factory-built homes. Japan leads integration with earthquake technology. Their modular buildings include seismic dampening systems built into each module. Performance in earthquakes exceeds traditional construction. Still, modular construction can't solve one specific challenge: bridges. You can't build a bridge in a factory and truck it to location. Too big, too heavy. At least that's what engineers thought. Then Japan did something that seemed to violate physics. Highway 7 outside Tokyo carries 80,000 cars daily. The bridge needs replacement, structural fatigue after 40 years, cracks in support columns, weight limits reduced for safety. Replacing a bridge normally means closing the road for months. Economic impact: businesses along that route lose $500,000 per month from reduced traffic. Detours add 45 minutes to commutes. Thousands of workers late to jobs. Delivery trucks rerouted. Engineers shut down Highway 7 at 11 p.m. on a Saturday night. By 5 a.m. Sunday morning, a new 400-foot bridge was carrying traffic. 6 hours, not 6 months. The bridge wasn't built over the gap. It was built beside the highway. While traffic flowed on the old bridge, construction crews assembled the new one on land next to where it needed to go. Every piece fitted together perfectly. Tested, inspected, verified, all while cars drove past 50 feet away. Then at night, the move happened. Hydraulic machines lift the old bridge straight up, slide it sideways off the support columns, lower it onto trucks, haul it away. The new bridge sits on special low-friction bearings, material smoother than ice, coefficient of friction 0.02, regular surfaces 0.5 to 0.7. Synchronized hydraulic jacks push from multiple points. The bridge stays perfectly level as it moves. Any tilt could cause catastrophic failure. The entire 4,000-ton structure slides through the air like a massive drawer closing. Positioning tolerance, 2 millimeters. Get the alignment wrong and the bridge won't seat properly on support columns. GPS guidance systems track movement in real time. Sensors detect any deviation. Hydraulic pressure adjusts automatically. Once in position, workers bolt it to the support columns, connect the roadway surface, remove the machinery, open the road. Morning rush hour, traffic flows normally. This technique is called bridge launching. It's been used 200 times across Japan, Netherlands, and Switzerland. 0 failures, 0 injuries during installation. The bridges are actually more stable because they're assembled under ideal conditions. No working over water, no building section by section with potential misalignment. Move as one complete piece. Tokyo saved $4 million in economic losses from traffic delays. A traditional replacement would have required detours for 8 months. But bridge launching has limitations.
Only works for certain bridge types. Beam bridges, not suspension bridges, not cable stayed designs. Requires massive upfront planning. The assembly area beside the highway must support the bridge's full weight. Ground must be reinforced. Space must be available. Weather dependent for the actual move. High winds stop the operation. Rain creates safety hazards. The 6-hour window requires perfect conditions, and it's expensive up front. The hydraulic systems, bearings, and GPS guidance cost millions, only worth it for high traffic routes where closure costs exceed equipment costs. China has scale advantages in traditional bridge building. They build more bridges annually than the rest of the world combined. But Japan has the safety precision, Switzerland has the alpine expertise. Netherlands has the water crossing specialization. Different leaders in different categories. Yet all three techniques, 3D printing, modular construction, bridge launching, share one limitation. They're building with the same materials humans have used for decades: concrete, steel, glass. Some engineers asked a radically different question. What if the materials themselves could be revolutionary? What if concrete could heal its own cracks? Rotterdam, 2014. A crack appears in a concrete bridge. Water seeps in. Engineers inspect. The crack measures 0.4 millimeters wide, small but growing. Water expands when it freezes. The crack will widen every winter. Standard procedure: schedule repair work, close lanes, cut out damaged concrete, pour new material. Cost $50,000 to $200,000 depending on severity. 3 weeks later, engineers return for follow-up inspection. The crack is gone. Not patched, gone. The concrete healed itself. Scientists mixed bacteria into the concrete before it was poured, bacillus bacteria specifically. The bacteria sit dormant for years, waiting. When a crack forms and water enters, the bacteria wake up. They consume calcium lactate compounds mixed into the concrete. Their metabolic process produces limestone, calcium carbonate, the same material that forms stalactites in caves. That limestone fills the crack from the inside out, bonding the two sides together at the molecular level. The bacteria go dormant again once the crack seals, waiting for the next damage event. That Rotterdam Bridge is 10 years old now, monitored continuously. Cracks that appeared in year 2 have completely disappeared. The concrete is stronger now than when it was first poured. Traditional concrete bridges need major repairs every 10 to 15 years. Costs range from $2 million to $5 million per repair cycle. This bridge has cost $0 in maintenance. The bacteria-infused concrete costs 20% more up front, but over a 50-year lifespan, it saves millions. Long-term analysis: a traditional bridge costs $8 million in repairs over 50 years. The self-healing bridge added $200,000 to construction costs. Net savings, $7.8 million. But living systems inside concrete raised questions. What if the bacteria die? What if they run out of food? What if freezing temperatures kill them? 8 years of data answered those questions. The bacteria can survive dormant for over 200 years. They've been tested in laboratory conditions simulating centuries of inactivity, still viable. The calcium lactate food source is embedded throughout the concrete, enough to heal cracks for the bridge's entire expected lifespan. Temperature testing showed survival from -20 degrees Fahrenheit to 140 degrees Fahrenheit, well beyond normal environmental ranges. Germany took biological construction even further. Hamburg, 2013, the BIQ House, the world's first algae-powered building. The exterior walls are glass panels filled with water and living algae cultures. Winter operation: algae absorb sunlight and produce heat through photosynthesis. The heat transfers to the building's water-based heating system, natural solar collection. Summer operation: the algae grow thicker in response to intense sunlight. They block more light, keep the building cooler, a self-regulating natural shade system. When the algae grow too thick, they're harvested. The algae biomass is converted into biofuel through anaerobic digestion. The building produces its own heating fuel. It's been operational for 11 years. Energy costs are 30% lower than comparable buildings. The algae system requires minimal maintenance. Water added monthly, nutrients added quarterly, harvesting twice per year. Total maintenance cost over 11 years, $18,000. Energy savings over the same period, $440,000. The system also captures carbon dioxide. Algae consume CO2 during photosynthesis. Exact capture rates aren't publicly available, but estimates suggest 2.5 tons of CO2 absorbed annually per building. But biological materials aren't the only advanced option. Some materials seem like science fiction. NASA designed a material for spacecraft re-entry. It can withstand 2,000 degrees Fahrenheit. Now it's in homes. It's called aerogel. Hold a blowtorch to one side of a thin aerogel sheet. The other side stays cool enough to touch with bare hands. Place a flower on top while fire burns underneath. The flower doesn't even wilt. This material is 95% air, lighter than styrofoam, but stronger than steel by weight. And it's the best insulator on Earth. A layer 1 inch thick provides more insulation than 6 inches of fiberglass. Buildings using aerogel insulation cut heating and cooling costs by 60 to 70%. Minnesota, 2018, a retirement home installs aerogel insulation during renovation. Heating bill before, $8,000 per month during winter. Heating bill after, $2,400 per month. Monthly savings, $5,600. Annual savings, $67,200. 5-year savings, $336,000. Installation cost, $180,000. Break-even point, 32 months, less than 3 years. After that, pure savings for the remaining life of the building. China invests heavily in construction material research and development, but Netherlands leads in biological building integration. Germany leads in energy-efficient materials. Different countries excel in different material innovations. Yet even advanced materials still require human workers to install them. What if the workers themselves were replaced? Singapore, 2021. A construction site operates 24 hours a day. No human workers visible after 6 p.m. Robots lay bricks at a rate of 3,000 per day. A skilled human mason averages 500. The robots don't take breaks, don't need water, don't get tired, don't make measurement errors. They work through the night. Floodlights illuminate the site, mechanical arms move with precision. Sensors detect positioning down to the millimeter. A high-rise apartment building in Tokyo was constructed with 80% robotic labor. Humans handled final inspections, specialized tasks the robots couldn't manage, problem solving when unexpected issues arose. The building finished 4 months ahead of schedule, came in 30% under budget. Construction robots don't replace workers entirely. They handle repetitive tasks. Humans supervise and manage complex decisions. But the labor market is transforming. Singapore's robotic construction sites pay workers 40% higher wages than traditional sites. Fewer workers needed, but they require advanced skills: robot operation, programming, maintenance, troubleshooting. A 50-year-old framer can't easily retrain as a robot technician. The skill gap is significant. Retraining programs exist, but they're underfunded. Most workers age out of the industry instead of adapting. Job displacement is real. One robotic construction site replaces 200 traditional workers with 50 technicians. Construction unions oppose automation for this reason. Political pressure in democratic countries slows adoption. Strikes, protests, legislative barriers. China faces less union resistance. State control overrides worker opposition. Robotic deployment accelerates faster. But geographic inequality emerges. Urban areas can support high-tech construction. Rural areas can't. The technology requires infrastructure, reliable power, network connectivity, skilled technicians within reasonable distance. Small towns get left behind. Singapore has the highest percentage of automated construction globally, but it's a city-state, high density, concentrated resources, wealthy economy. Scaling that model to vast countries with dispersed populations creates challenges.
Japan pays the highest wages for automated construction workers. They've addressed the skills gap with aggressive retraining, government-funded programs, industry partnerships with technical schools. Result? Older workers transition successfully. Employment remains high, even as automation increases. China has the largest deployment of construction robotics in absolute numbers, more robots than any other country,
but as a percentage of total construction, still relatively low. The country is too big, too many projects in remote areas where robotics aren't practical. The United States lags in adoption, fragmented regulations across 50 states, strong union presence in many regions. Higher labor costs make automation attractive, but regulatory barriers slow implementation. Different adoption patterns, different challenges, different solutions. Yet all these technologies, 3D printing, modular construction, advanced materials, robotics, are operational now. They work, they're proven, they're cheaper over time. So why aren't they everywhere? The answer involves a moment in 2019 when officials saw something that changed everything, and the barriers that still prevent widespread adoption. The real conflict isn't technology, it's politics, money, and power. Multiple sources confirm it happened. The exact location remains disputed. Some reports say Dubai, others mention Amsterdam, a few claim Shanghai. What matters, a delegation of government officials and construction industry leaders toured demonstration sites. These weren't novices, career professionals, people who built airports, managed billion-dollar highway projects, overseen skyscraper construction. They watched something that contradicted their entire understanding of what was possible. Most likely a 3D printing demonstration, a structure rising in real time, or possibly a bridge launch, a massive structure moving through the air in minutes. One official stopped mid-sentence, requested to see the demonstration repeated because the first viewing seemed impossible. The reaction wasn't polite interest, it was shock. Within 6 months, construction technology research funding tripled across multiple countries. Government contracts for modular housing accelerated. International competition intensified. The technology shifted from experimental curiosity to national priority. But if the technology works, costs less, and builds faster, why isn't it everywhere? 5 major barriers block adoption. Barrier 1. Regulations. Building codes are written for traditional construction, concrete poured into forms, wood framing, bricklaying, inspections at specific stages. 3D printed buildings don't fit existing codes. The inspection process is different. Load calculations are different. Fire testing protocols don't apply cleanly. Getting approval requires special variance requests, months of review, different rules in every city, every county, every state. In the United States, 50 different state codes, thousands of local modifications. A method approved in Austin might be banned in Houston, 150 miles away. Standardization doesn't exist. Barrier 2. Financial structures. Insurance companies won't cover unproven methods at reasonable rates. They need decades of actuarial data. 3D printed homes have 5 years of track record, not enough. Higher insurance premiums eliminate cost savings. Banks won't provide mortgages for experimental homes. Resale value is uncertain. If the buyer defaults, can the bank sell a 3D printed house? Appraisers don't know how to value these properties. No mortgage availability means no buyers. No buyers means no market. In U.S. cities, land costs represent 50 to 80% of total housing cost. A $4,000 printed house sounds revolutionary, but if the land costs $200,000, the savings disappear. Permitting adds $50,000 or more in major cities. Connection fees for water, sewer, and electricity run $20,000 to $40,000. The $4,000 house becomes a $270,000 house after all real costs. Mexico's example works because rural land is cheap, labor costs are lower, building standards are different. That model doesn't translate directly to expensive urban markets. Barrier 3. Labor opposition. Construction unions actively resist automation. Jobs disappear. Political pressure follows. In democratic countries, unions have power, strikes, campaign contributions, legislative influence. Politicians face a choice: Support construction innovation or support construction workers? Most choose workers. Voters matter more than efficiency. China doesn't face this barrier. State control overrides union opposition. The government mandates adoption. Workers comply or find different jobs.
Authoritarian advantages in infrastructure development are real. Barrier 4. Corporate control. Icon, Cobod, Apis Core. These companies hold patents on 3D printing construction technology. Licensing costs are high. A contractor can't just buy a printer and start building. They need training, certification, ongoing licensing fees. Patent wars slow innovation. Companies protect intellectual property, sue competitors, block open source alternatives. Chinese tech transfer restrictions work both ways. Western countries can't easily copy Chinese methods. China restricts technology exports, protects domestic advantages. Barrier 5. Cultural resistance. People reject homes that look weird. Resale concerns are legitimate. Will buyers want a 3D printed home in 20 years? Post-World War II prefab housing created lasting stigma. Those buildings were low quality, they deteriorated, became associated with poverty. That perception persists. Developers hide modular construction methods, design exteriors to look traditional. The innovation becomes invisible to maintain market acceptance. Europe wants historic aesthetic preservation. American suburbs want uniformity. Asian cities want modern glass towers. Architectural diversity matters to buyers, but new construction methods often produce similar-looking buildings because templates are reused for efficiency. So where does China actually lead? Scale, pure volume. They build more modular housing than the rest of the world combined. Government mandate enforcement. The 30% prefab requirement is real. Projects that don't comply don't get approved. Vertical integration. Chinese companies control entire supply chains, materials to robotics to construction. Investment. Construction technology R&D spending exceeds combined US and EU budgets. Export capacity. Belt and Road projects spread Chinese methods across 60 countries. But UAE leads per capita adoption. Netherlands leads policy innovation. Japan leads safety technology. Singapore leads automation percentage. China leads scale and speed, not every category. The competition is multidimensional. And what's being tested now makes everything we've covered look primitive. Labs in 3 countries are testing construction methods 50 times faster than current 3D printing. One uses sound waves to position materials in midair, acoustic levitation, building without touching anything, no robotic arms, no physical contact. Early tests show potential but face massive energy requirements. Another approach, swarm construction. Thousands of tiny robots instead of one large machine. They coordinate like ants building a colony, adapt in real time to changes. Iceland ran tests in 2022. A 200-square-foot structure assembled in 90 minutes. The robots adjusted their behavior when one unit failed, compensated automatically, no human intervention. These aren't concepts, they're active experiments with documented results. Timeline predictions. Industry analysts estimate 25% adoption of advanced construction methods by 2030 to 2035. Regulatory changes lag behind. Building codes expected to catch up by 2028 to 2030. Cost curves favor new methods by 2032. 3D printing becomes cheaper than traditional construction everywhere, not just in specific cases. Disaster relief applications are accelerating. Haiti, after the 2010 earthquake, Icon printed replacement homes within weeks instead of years. Florida is testing hurricane-resistant 3D printed homes. Curved walls deflect wind. Solid concrete construction resists debris impact.
California could have housed wildfire victims in weeks. Instead, families spent months in hotels. The technology existed. Regulations prevented deployment. Lives saved, not just money saved. Environmental pressure is driving faster adoption than economics. Construction generates 38% of global CO2 emissions. These new technologies could cut that by 60%. Self-healing concrete alone saves millions of tons of cement production. Cement is the biggest carbon contributor in construction. Algae buildings actively capture carbon. The climate case is stronger than the cost case. But there's one technique currently restricted in most countries: materials that rebuild themselves without any external input, structures that grow stronger over time, adapt to stress patterns automatically. 3 countries are testing it right now. The structures adapt without human input. They learn. One engineer called it biological construction without biology. Another said it's closer to growing a building than making one. The patents are sealed. The locations are undisclosed. The implications are enormous.